Hello, welcome to a new session on this course on Introduction to Embedded System Design. In this lecture, we are going to consider the ecosystem that a microcontroller requires for its operation, and once we complete that, we would look at the power supply building block as part of the 6-block representation. So, let us start. What are the elements of a microcontroller ecosystem? Meaning, what does a microcontroller require to function independently? As you know now that a microcontroller is a complete computer on a single chip. It is able to perform whatever it is programmed to do, just if few elements of its required ecosystem are provided to it. What are these elements? So, I title it as Roti, Kapda, Makan and Internet for a microcontroller. This crazy sounding title has been derived from a previous slogan which said, for human survival you need three things: roti, that is food, kapda, clothing and housing. In recent times, even the lowest level of society requires internet for survival, and therefore a human being requires four things: food, clothing, housing and internet. And we found a interesting parallel that even a microcontroller requires four such things. And what are these four things for its survival and active working? It requires a clock. We will see why it requires a clock. It requires a reset circuitry. Usually that reset circuitry is integrated in the microcontroller itself. It also requires a power supply, perhaps different from the power supply requirement of the rest of the embedded system application. And then it requires a mechanism to download code from the development platform, which often is your desktop or laptop computer, into the memory of the microcontroller. So, we have to ensure that the microcontroller is provided for with these elements, then only it can function properly. And if the microcontroller can function properly, then the rest of the embedded system can function properly. So, let us start with the first element of this ecosystem, the clock subsystem. Why do we need a clock? Can we design microcontroller systems without a clock? Most of the time you would have seen that an analog circuit does not require a clock. But microcontroller is different because it is an example of a digital circuit. Now, digital circuits can be designed in two ways: what is called as asynchronous sequential circuits, and the other type is synchronous sequential circuits. So, any digital circuit or system could be designed in two ways: synchronous sequential mode and asynchronous. Now, asynchronous sequential circuits are very efficient. They consume very little power, but they are very difficult to design and even more difficult to debug and verify. And therefore, almost 99% of all logic circuit implementations are of this variety, synchronous sequential. Now, the term here synchronous means that it uses a clock circuit for its operation, and therefore you need a clock. So, this defines or this justifies the need of a clock, because a microcontroller is an example of a synchronous sequential circuit. Then the next question arises. So, we have answered this. The next question arises as to what should be the clock frequency. Now, there are two diverging arguments that the clock frequency should be as low as possible. Why? Because in a CMOS logic circuit, the power dissipation consists of two parts, the static power dissipation plus the dynamic power dissipation. The static power dissipation is a function of the technology, the way the system was built, but the dynamic power dissipation in a CMOS circuit is equal to the capacitance that the circuit sees at its load into the frequency of operation into the VCC squared, which means the dynamic power dissipation is directly proportional to the frequency of operation. So, if you increase the clock frequency, that would consume the battery faster. If you double the clock frequency, it will double the power dissipation, which means it will empty the storage, that is your battery, in half the time. Now, this is one argument why you should keep the clock frequency low. What is the argument towards keeping the clock frequency high? Well, if the clock frequency, the performance of a computer is directly proportional to the frequency. For a given computer, if you double the clock frequency, then it will execute the same program in half the time. And so, these are two arguments which are pulling in opposite direction, and therefore, as a efficient embedded system design, you must strike a balance, one which optimizes the power dissipation and the other side where the frequency is high enough for the system to work properly. So, we have seen why we need a clock, we have seen what should be the clock frequency, we have also considered the implications of this clock frequency, that if we keep the clock frequency very low, it will certainly provide a longer operation on a given battery, but its implication could be that it may not be able to fulfill the requirements, the timeliness of a program, and therefore, you may want to increase it. And as a designer, as an engineer, you would have to strike the right balance, trade off between low enough frequency to keep the power down and high enough for it to perform its designated task. What are the various topologies for generating this the clock for microcontrollers? Now, if we look at the pinout of typical microcontrollers, you will see that it offers you a couple of pins on which you can connect an external component such as a quartz crystal, and oftentimes it also has an internal RC oscillator. Let us see what these circuits look like, or in general how do we create a clock signal. So, one simple method we already discussed in a previous lecture was to use a Schmitt trigger with a capacitor and a resistor to generate the frequency. This could be used. Another one, you could use a very popular IC called the 555 timer IC. It's a 8-pin IC. You connect 4 and 8 pins to VCC. Then you have pin number 7, you connect a resistor R1, and then pin number 2 and 6, you short them, and you have another resistor, this is R2, and from here you put a capacitor to ground. See, you have pin number 5 which you decouple and put a capacitor, and on pin number 3 you get the output voltage. The frequency of such a topology is 1.44 divided by R1 plus 2R2 into C, and you can tailor the values of the resistances and the capacitors to get your required frequency. Now, what happens is a typical 555 oscillator timer will require a power supply in the range of 4.5 volts at least to 15 volts for operation, and if your microcontroller also operates in a similar power supply range. You do get microcontrollers which work at 5 volts, then you could use a 555 timer. In case you have a microcontroller which requires a lesser operating voltage, say 3 volts, then instead of a regular 555 timer, you can use a CMOS variant of this timer called 7555 with identical pin configuration, but with a much diverse power supply requirement. It can operate from 3 volts to 18 volts. So, you could perhaps use such a external clock generator. The output of this or output of this would be connected to your microcontroller. Here is a microcontroller, and you may have pins called X1 and X2 on which, if you do not want an external clock generator, then you connect an appropriate crystal, a quartz crystal between these two pins. It may also require you to use some small value capacitors. These will be mentioned in the data sheet of your microcontroller, and you must follow those specifications. In case you do not want to use this crystal, then instead of this crystal, the output of such a clock generator 1 or say 555 or 7555, this output could be connected to X1 or X2 input as mentioned in the data sheet. There is another interesting method of generating clock, and that is by way of what is called as a ring oscillator. A ring oscillator, as the name suggests, is a ring of components. In fact, it uses a NOT gate, an inverter, an odd number of inverters. So, if I take 3 inverters and I put them, connect them like this, power it with appropriate supply voltage, then at any point here it will show oscillations, and the frequency of those oscillations will be equal to 1 upon 2 times the delay period of this device into n. In this case, n is the number of elements, in this case 3. From the data sheet of this inverter, you can find out what is the delay time. For typical TTL family components, TD is of the order of few nanoseconds. Therefore, you might get maybe 1 by 2 into 3 into say 5 nanosecond. So, this is about 1 by 30 nanoseconds, and that will give you roughly 30 megahertz of operation if you want a high frequency. Please note that 555 or 7555 timer cannot provide a very high frequency beyond a couple of megahertz, and so it may not be suitable for some applications. Anyway, these are the methods of creating external clock signals with which you can feed your microcontroller. It turns out that such a need is usually not required. Such a topology is not required. Why? Because microcontrollers have built-in oscillators. They have built-in RC oscillators, and you can choose, do you want to use a regular oscillator or do you want to use an internal RC oscillator. The internal RC oscillator, you can imagine, would be of this type, and therefore, since it uses these R and C to provide the clock frequency, the variation in the resistor and capacitor values will change the frequency, and therefore, it may not be used for very accurate measurement of time. But if your application is okay with a little degraded performance of the clock generator, as in it is not as accurate as you would want, then this could be a good low cost solution. In case you want higher precision in time measurement, then you would use this option, where on the designated pins of the microcontroller X1 and X2, you would connect a crystal of appropriate frequency together with some capacitors if the data sheet says so. And typically the values of these are of the order of 10 to 20 picofarads here as well as here, and the crystals could be in the range of the lowest crystal that you may get. The lowest crystal incidentally happens to be 32768 hertz, and I will come to this I have also mentioned it in the past, but we will go through this again, and going up to 1 megahertz, 2 megahertz and so on, going up to few tens of megahertz, 20, 30 megahertz crystals may be available, and you could use them for determining the clock frequency. The oscillator part, the active part of the oscillator is inside the microcontroller. Therefore, all you need is external couple of components, and this provides the source of clock. As I mentioned in the previous lecture, if the microcontroller offers clock scalability, then you should start with the lowest clock frequency crystal, because internally you could use a multiplier to increase the clock frequency to a high value that you would want at given point of time. And if you so desire that you do not require a high enough clock frequency, then you can scale it down to the lowest value, which would be the crystal value, in this case 32768 Hertz. So that would be a good choice for a crystal to be used in such microcontrollers which have this option of runtime clock scalability. So now we have seen what topologies for clock generators, and also what are the desirable features of the clock generator. We have seen that we would like to have a clock generator which we can, the frequency of which we can change at runtime, but this is usually inherent and built-in feature of a microcontroller, and you must evaluate whether your application requires such a function. Then you must choose a microcontroller which offers that functionality. Apart from the clock frequency that is required by the microcontroller, you require an additional clock, a complete clock system, and that clock system is called a real-time clock. A real-time clock is a dedicated function, dedicated circuit which provides a certain functionality which is to maintain real time. So, RTC maintains real time, that is it can be used to know what is the current time of the day at whichever location you may be. Of course, for this it requires a source of frequency, and usually the source of frequency is a crystal, and that crystal is usually 32768 Hertz, and this frequency, this seemingly odd number is not that odd for computer and electronics engineers, because this number is exactly equal to 2 raised to power 15 is equal to 32768. Historically, these crystals were used in digital watches when they started appearing in late 60s and early 70s, and this low enough frequency was chosen because again these clock circuits were CMOS based, and the power dissipation had to be kept low because they were battery operated, and therefore balance was achieved that the frequency should be low enough and the crystal should not be large enough. Therefore, they found that 32768 is a good trade-off. It is small enough in size, and it would lead to relatively less power dissipation. Although for record I may mention here that the very first digital quartz crystal based clock that came on the market was a Seiko clock, and it actually used 8192 Hertz crystal. But subsequently the common frequency of use was this, and this frequency has since been adapted and adopted for use with RTC chips. Usually this is a 8 or 16 pin IC. It has a power supply pin. It also has a battery backup, so you would have additional pin called VBAT, and it would have a mechanism to communicate with the microcontroller. Usually this would be the I2C or SPI interface. We have discussed that communication protocols are inherently, some of the communication protocols are inherently available on certain microcontrollers. So these microcontrollers could talk to this real-time clock chip through these communication protocols. It may also have a alarm pin, so that when you program this real-time clock to wake you up on certain alarm, when that time is reached, this signal, the alarm pin would go from 0 to 1, and this could be used to interrupt the microcontroller to do whatever was expected to be done. The frequency, as I mentioned again, is 32768 Hertz. The accuracy of the crystal here would determine how good the real time is being maintained. And typically these crystals have a temperature coefficient which is of the order of few parts per million per degree centigrade, and therefore traditional real time quartz crystal based real time clocks offer roughly a drift of few seconds per month kind of numbers. If you want even more accurate maintenance of time, then there are two options. One is to regularly correct the frequency or the time that this clock is maintaining, and one way to do that is to get the actual time from the internet. There are services which offer that time, and in fact your PC and laptop often fetch the time from the internet sources and correct the clock in case it has drifted. The other is to use a more accurate source of clock, and one way to do that would be to maintain this crystal and this circuit at a constant temperature. Let us go back to the presentation to see what we are talking of. You can stabilize the clock using a technique called TCXO, meaning temperature compensated crystal oscillator. This is basically a small enclosure where the temperature of that enclosure is maintained to a fixed value irrespective of the outside ambient temperature, and this ensures that the crystal does not drift. Another method uses unfortunately this method consumes a lot of power to maintain that temperature. Another method uses a temperature sensor and a varactor diode, and the way these crystals work is the circuit diagram of a crystal oscillator is like this, that you would have an inverter and you would have a large value of resistor, another resistor here, and you would have a crystal between these pins, and you would have couple of capacitors, as I mentioned, low value capacitors. Now this is typically say 10 picofarad, this is also 10 picofarad, and say this could be say 1 megahertz. Now if I change this crystal, if I change this capacitor, I can load the frequency operation and I can change it a little bit. Similar way I can add therefore instead of changing it manually, I could add a varactor diode. Say a varactor diode is nothing but a diode which is operated in reverse bias. I need to decouple the varactor diode here by using a large capacitor, and I apply a bias voltage here, say some V bias. By changing the bias voltage, the capacitance between these 2 points can be changed, and therefore the effective capacitance as seen at this point A would change, which would tweak the frequency operation. And so in many circuits where they want to offer a better temperature stabilization, they use a temperature sensor to monitor the temperature, and to compensate for any variation in temperature, they change the bias voltage on this varactor diode which has been placed in parallel to one of the capacitors of the crystal, so as to maintain a fixed clock frequency. So these are various methods of having higher accuracy clock frequency signals in applications where you require more precise measurement than what would be available with just the quartz crystal or with a RC oscillator.